Hi guys, before we start up with today's topic, there's a small announcement. Now I skipped a few parts in the Bayes theorem part, that is the extension of Bayes theorems part. We have already dealt with one hypothesis and two evidences case, and I've skipped one hypothesis, multiple evidences, chain evidence, multiple hypothesis, single evidence, multiple hypothesis and multiple evidences cases. The reason being they're pretty much similar to whatever you have seen in the case of one hypothesis and two evidence cases. And all those people have done their assignment well, they would know pretty much what chain evidence is all about. So what I want you guys to do is look at page number 313. There's a portion called as multiple hypothesis and single evidence. There are three equations written there, 9.15, 9.16 and 9.17. I want you guys to write in your own words what you understand by those equations and how do you think they might have come into existence over there. You don't have to prove anything, just write in your own words what you understand. Anyway, so that is the announcement. So that will be your second question in your assignment number 2. So let us head into today's topic. That's called probabilities in rules and facts of a rule-based system. Now traditionally in a rule-based system, we have observed that the left-hand side, that is the conditions, and the right-hand side, that is the conclusions, they both are absolute. That is, if you know that A is true for sure, then B is also true in the case of A implies B. But in reality, that is not always the case. So inferences or even facts are to some degree uncertain or probabilistic. This is particularly true when facts in a rule-based system represent evidence and rules represent hypothesis, just like in our case. So an example could be a car expert system. So in that case, say for example, you observe that there's a brake failure. Now the reason for brake failure could be various things. So let's say 80% of the cases where we have a brake failure could be due to a wire failure. And let's say 10% of the cases it could be because the engine has stopped. Or maybe 5% of the cases it could be some miscellaneous thing. So over here in real cases, we do have to associate our rules with some kind of probabilities. So in this class, we're going to look at all these rules with probabilities. So here you have an example. So there is a fact given, which is saying battery is dead 2% of the time in a randomly picked computer. So how do we represent this in the case of a rule-based system? So that is what we're going to look at. Anyway, so this says battery dead computer 0.02. So this is a predicate right here, and this is associated with the probability 0.02. So that is pretty much it. Now you could even have probabilities associated with rules. So how do you deal with that? So let us look at this example. It says if 20% of the time a computer doesn't work, it is true that its battery is dead. So in this case, if you observe this one next to this computer not work, so what this says is that I'm assuming that the computer is definitely not working. So I was associated 100% probability with it. So if that is the case, what it is saying is that 25% of the cases it's because the battery is dead. Remember, this is the syntax that you would use in the case of prologue. So this would be your condition and this battery dead computer would be your conclusion. Anyway, let us look at another thing. Now this is pretty straightforward. It says that probability of a battery being dead is same as circuit being faulty. So you associate the same value P with both your conclusion and your condition. Now contrast that with something like this. Now this rule right here, it says if 30% of the time when computer has circuit problem, the battery is dead. So this time around, I'm not considering that the computer definitely has a circuit problem. I'm considering that it might have a circuit problem. So I associated this with the probability P. So in that case, in 30% of the cases, the battery is dead. So I have associated this other part with P dash. And the relationship between P dash and P has turned out to be 0. p dash equal to 0.3 into p. So you could replace the same thing here. It means the same thing anyway. So why are we dealing with all this stuff? Now, this is of the utmost importance here. Now, how do we combine all these probabilities? Now, when a big rule-based system like Myson, we know that we are supposed to combine all those rules in order to like judge something. So we have two kinds of combinations available. One is called as an AND combination. The other one is called as an OR combination. So AND combination goes pretty much like this. So you just multiply all the probabilities. So when do you use an AND combination? You basically use an AND combination for all your conditions. So say for example, this circuit problem here is one of the conditions. Maybe this has another condition, let's say B, and B has, let's say, P double dash as another probability. So what are you supposed to be doing to combine these two probabilities? So that is where your AND combination plays a key role. Now what is an OR combination? Now the formula for it is present right here, so I do not have to like go through this thing. Now when do we use OR combination? Now battery dead, this is one of the rules for battery dead. Now there can be various other rules, right? So in that case, so this can be the conclusion in various other cases. So how do we combine all those conclusions? That is where OR combination is used. So this OR combination is used for conclusions. This AND combination is used for conditions. So let us try understanding this better with an example. So here is an example. It says battery dead computer. It has a probability P, and the conditions are computer circuit, fault P1, battery old, probability P2. So how do you combine these two? You use an AND combination. You look at this part, AND combination, you directly multiply these probabilities. And there's another thing. Instead of representing in this manner, you can also represent it this way. So whenever you have an AND combination, you usually write your rules like this, but you can also use this representation. So that's why I have an OR here. Anyway, let's look at another example, this time for OR combination. So just like I told you, if you have multiple rules for the same conclusion, like let's say compute 0.4 as is saying that A is the condition, here B and C are the conditions, here A and D are the conditions. So in this case, how do we combine these probabilities? For that, we use an OR combination. Now once again, this was the formula that we have used here. We wind this topic up with another small example. So here you have multiple rules whose conclusions are compute, and there is this rule which uses an AND combination because there are two probabilities involved here. So what do you do in this case? So for this probability you use an OR combination, this probability you use an OR combination, and over here you use an AND combination, and then for the net answer you use an OR combination. So finally this is what you would be ending up with. We also have formulae for handling negative probabilities that is given over here. It's pretty much straightforward, so I'm not going to go through with any of the examples. So that is it that we have here. So in the next chapter, or rather next topic, we'll be looking at Bayesian belief networks. Thank you.